talk about that the title has been changed. Yeah. Of graphs with bound matching numbers.
Thank you very much for inviting me here. It is very honorable to give a talk in IBS Discrete Math Seminar. And the title of today's talk is a little bit changed. I did not recognize it. The title is a topology of complexes of graphs with bounded matching number. And this is a joint work with my advisor, Andreas Olsen. So first, let me briefly overview the presentation. First, I'd like to introduce the non-matching complex. That is the simplicial complex consisting of the graphs, subgraphs of the given graph G, which has a bounded matching number, that is matching number less than K. And the purpose of this presentation is to show how to derive the topological information of the non-matching complex. So to do that, we use the following tools. So first tool is the so-called discrete Morse theory, and the second tool is the Gallai-Edmonds decomposition in the matching theory of graphs. And after that, I would like to briefly sketch the proof of the main theorem on the topological properties of the non-matching complex, and then I will apply that topological result to the rainbow matching problems. And we will have some discussions, and I will give some of the problems. So I will start the first part. So let us recall that the simplicial complex is simplicial complex on the ground set E is a family of subset E such that it satisfies the hereditary property. That is, if sigma is a face of K and tau is a subset of sigma, then tau is also a face of K. And especially if K consists of just the graphs on a fixed vertex set, we call it a graph complex. And in this case, since the vertex set is fixed, we identify every graph with its edge set. And we will use this convention for this presentation. And there are various graph complexes whose topological properties have been extensively studied. For example, there are many graph complexes. For example, the graphs of matchings, forest, bipartite graphs, non-Hamiltonian graphs, not K-connected graphs, and T-colorable graphs, and so on. So basically, every monotone graph properties can define graph complexes, and graph complexes can define monotone graph properties, and vice versa. And in this talk, we focus on the non-matching complex defined by the following. As I said before, the complex NMKG is defined by the set of all subgraphs of G such that it has a bounded matching number. That is, the matching number is less than K. So, yeah. And the following result is the previous result by Linusson et al. And the statement is the following. If G is a complete graph or the complete bipartite graph, then it is a homotopy equivalent to a wedge of spheres, where if we take the complete graphs, it is a wedge of spheres of dimension 3k-4, and if we take the complete bipartite graphs, it is a wedge of spheres of dimension 2k-3. So anyhow, I wanted to generalize this result to the arbitrary graphs. But so we can just see that actually, if this is a homotopy equivalent to this, then if we just consider the homology group of this simplicial complex, then the non-vanishing homology is concentrated into a single dimension. So for the dimension of the spheres. But for general graphs, it does not hold. So, for example, there is a following example like this. So, actually, it could be generated by the computer software. And in general cases, the non-vanishing homology is not concentrated in a single dimension. So, for this graph, if we consider the non-matching complex of the when k equals 3, this has a non-vanishing homology in dimensions 4 and 5. So, in other words, it is somewhat hard to just directly generalize this result. So rather than doing that, we focus on the upper bound on the dimensions of non-vanishing homology. That is what I'm trying to. That is what I basically try to do, and we can just say that for this example, for the example of complete graphs and complete bipartite graphs, we can have the upper bound on the non-vanishing homology. In the so for complete graphs, it is 3k minus 4, and for complete bipartite graphs, it is 2k minus 3. I like to generalize this result. So this is the main statement of main theorem. Before introducing the main theorem, I'd like to briefly introduce the topological notion. So a simplicial complex K is called near the Leray if the reduced homology of the ith dimension of the link of the sigma, where the for every non-empty phase sigma becomes vanishes. So it vanishes for every I at least d, where the link is defined by the all the phases in tau, such that the tau union sigma is in K and tau intersection sigma is empty. So we can just consider link as a generalized notion of the neighborhood in a graph, on a graph. And the main theorem states like the following. This non-matching complex is near 3k minus 4 Leray. Note that, so this complex, so we, even if we fix the vertex at V primarily, but it does not depends on this topological near the Leray property does not depends on the number of the vertices, but only depends on the matching K, matching number K. And further, if G is bipartite, non-matching complex is near 2k minus 3 Leray. This is our main theorem, and as a corollary, as I said, it could be this corollary can be considered as a little bit generalized statement of the Linusson's previous result. The complex NMK G has a vanishing homology in all dimensions bigger than or equal to 3k minus 3. And for bipartite graph, the lower bound becomes 2k minus 2. Yes, so it gives a lower bound for vanishing homology, so upper bound for non-vanishing homology. So it can give some this corollary. Actually, this corollary can be deduced from this main theorem by some simplicial homology argument. So we will focus on this theorem, this main theorem. And actually, near the Leray property is a hereditary. So if L is an induced, so it means that if L is an induced subcomplex of K, and K is near the Leray, and L is also near the Leray. So if we could prove this theorem for complete graphs and complete bipartite graphs, then actually all the non-matching complexes for the arbitrary graphs can be considered as an induced subcomplex of the NMK for complete graphs or complete bipartite graphs. So we can get this main theorem for every graph. So we will focus on only complete graphs and complete bipartite graphs also. And so as a main tool, so we use the discrete Morse theory and the Gallai-Edmonds decomposition. And I'll introduce these tools in the next slide. Okay, so we will introduce some tools from now on. And first tool is the discrete Morse theory. So this is the brief introduction to the discrete Morse theory. Discrete Morse theory is formulated by Foreman in 1998, Robin Foreman in 1998, and the original formulation is somewhat different, but the contemporary, so the most common contemporary setting is the following, I think. So let F be a family of so this is a typo, sorry. So the F be a family of subsets of E, and so we call so an element matching on the family F is a family M of disjoint pairs sigma and tau with the sets in F, sigma tau in F, such that sigma is a proper subset of tau and the size difference is just 1. And as a directed edge, it is just heading to the from the smaller set to the larger set, right? And the DFM is defined by the union of the pairs. So first it has an M, and for the other pairs, so we also define the sigma and tau. So the set of pairs such that the sigma and tau satisfy the following properties. So now the containment is reversed. The tau is the subset of sigma, and as well so sigma and the size difference between sigma and tau is 1 as well, and tau comma sigma is not in the matching M. So for this set, we can easily see that actually it is the direct when we consider it as a directed edge. So the element is, so when we consider the element of this family as a directed edge, it just directs from the larger set to smaller set. So we can consider this DFM as a directed graph. And sets in F not matched by M are called critical sets. And as a directed graph, if DFM is acyclic, then the matching M is called an acyclic matching on F. Then the theorem by Foreman, so actually this theorem is called the main theorem of the discrete Morse theory, says the following. If there is an acyclic matching of a simplicial complex K with Ci I-dimensional critical faces for each I, then K is a homotopy equivalent to K prime, where K prime is a CW complex with Ci I-dimensional faces for each I. So actually this theorem is not only for simplicial complexes, for arbitrary cell complexes. And if you are not very familiar with the CW complex, then you can just consider it as a generalized simplicial complex somehow. I'll give some example. The first example is very simple. So we consider the Boolean post. Actually, for some reason, when we consider simplicial complex, we assume that the empty face is contained in the simplicial complex. So the 2 to the E is just a power set of E, and E contains all the subsets of E, and actually as a simplicial complex, it corresponds to the ball. So the size of E minus 1 dimensional ball. And then we can find a complete acyclic matching like this. And so we can easily see that actually, so for any fixed E, we can easily see that actually this is a complete element matching, where complete means the perfect matching. But how can we show that this is a cyclic matching? So actually, there is a very elementary criteria which is called the cycle lemma. But I did not state the cycle lemma in here, but I just draw the diagram.
Can you remind the definition of acyclic?
Acyclic match, okay. Acyclic matching is if this directed graph is acyclic, so actually this is just we can just consider F as a poset, right? And prime. So initially, so we just consider the Hasse diagram where all the edges are directed to downwards, but we just reverse the direction for edges in M. So maybe I can show this example. So
DKM is so it's orientation of the directed graph.
yeah. DKM is considered as directed. Yes. So we just consider. So this can be recognized as a Hasse diagram of poset, right? And actually, initially all the edges are directed downwards. But for the matching, so for the edges in matching, we just reverse the direction to the upwards. This is the directed graph DKN. Yeah. Yes. And so if there is if this directed graph is acyclic, then we call that M is acyclic matching. Any other question? Okay, so I'll go to this example again. So how can we show that this matching is acyclic? So actually there is an elementary simple criteria which is called the cycle lemma, and it can be stated as follows. Suppose that the directed graph DKN is not acyclic. It means that there should be a directed cycle in that directed graph, right? And that directed cycle should have a form like this. And so first, so these red edges represent the edges in M. The other blue edges, which directed downwards, is not in M. So edge is not in M. And so these edges alternatingly appears in the directed cycle, and the bigger sets, bigger matches set, that is a tau 1 to tau r, have the same size, and also smaller matches set from sigma 1 to sigma r has the same size. And for example, this directed cycle can be described by the added element from sigma 1 to tau 1, and the deleted element from tau 1 to sigma 2. Okay. And so if we follow this directed cycle, if x1 is added, for example, k times, then x1 should be removed k times. Yes, right. So because anyhow, this is a directed cycle on the set. So if x1, the same element x1 is so added k times, then this should be removed k times anyhow. And this is just this is a cycle. And this is actually complete acyclic matching. And suppose not, if this is not acyclic matching, then there is a directed cycle like this. And since we are using this kind of matching, so all the x1 to xr should be E. Then by what I said before, all the y1 to yr should be also E. Then actually it should not go to the other element, but it should go back to this element, go back to the original element. This does not happen. This cannot happen in the Boolean process. So there are no parallel edges in the directed graph we are considering. So this is a simple example that I would like to introduce. Any question about this example?
When you define the matching,
yes.
Do you also mean that the ends are disjoint?
Yes, ends are disjoint. So it is a family of disjoint pairs. Disjoint pairs. Yeah. Okay. So any other questions? So it is basically just a matching. Yeah. But only additional condition is the size difference is 1. If there is no question, then I will go to the slightly more difficult, complicated example. And actually, this is a poset. So phase poset of a boundary of an octahedron minus 2 antiphoda classes. So this is the phase poset of this simplicial complex. And so as I said, these red edges represent the matchings in M, and these blue edges are non-matchings. So non-matched edge. So non-matching edges. Okay, and we can easily see this this is acyclic matching because this is the acyclic directed graph, and there are two elements which are not matched by n, and they are so critical sets. We can draw this matching in a simplicial complex like this also, and actually this red edge, for example, this red edge represents the matching between this thick green edge 1, 2 and this light green face 1, 2, 4, and so on. This matching actually can describe the describe the way how we can construct a homotopy equivalence between this original simplicial complex to the desirable CW complex actually. And so first we consider these red edges in the outside, so between the green ones. Then we can these thick green edges follow this red edge until they meet this boundary. For example, for 1, 3, they go by the red edge direction, and they meet the boundary 1, 5 union 5, 3. Also the same as 1, 2 goes to until they meet 1, 5 union 2, 4, and so on. So if you are familiar with the simplicial complex terminologies, then it is called the collapse. So this is contained the unimaximal faces, so just remove the face. Yeah. So actually we should consider the blue edges. So similarly we can consider the same argument as in the blue edges in the middle 4, 5, 5, 6, 4, 6, and the light blue faces in the middle. So we can collapse them. And in the same argument, we can collapse the green faces so that we can have this. And for the remaining faces, actually 2 and 2, 4 is a critical faces. And for the other faces and vertices, for other edges and vertices, so this, for example, this 4 is following this edge, following this red edge until it meets 1. So it is basically contraction in a graph theory. So it becomes like this. So 4 goes to 1, and 1 and 4 are identified each other, and so on. So it contracts the edge also, and it becomes so 4 and the vertices 1, 4, and 5 becomes identified, and there are 2, 4, the edge 2, 4, and 2 are still remains, and so on. This process is done until 1 and 4 and 5 meets 2. So finally, it becomes the circle, like this. This is a kind of the continuous deformation from the original simplicial complex to this CW complex, consisting of 2 critical faces. One is the vertex 2 originally, and the other is 2, 4. Yes, this is an informal description of the examples, and so we can use the discrete Morse theory to derive the main theorem. So let us recall the main theorem here, and the actual theorem we want to prove is this theorem. Given a non-empty graph H, the family consisting of all graphs in the complete graphs. Since we are considering the complete graphs, so such that it contains H and the matching number is less than K. So this family has a cyclic matching where critical sets have size 3K minus 4 plus H. And actually this family is isomorphic to this link as opposites each other. So we can also, so by this result, we can also find a cyclic matching for this link. And since this link, since this have no critical sets, bigger than or equal to 3K minus 3 size, so we can conclude this main theorem. Because there are no, so the homotopy equivalent CW complex that does not contain any 3k minus 4 dimensional cell or above. Yeah, so this is the basis. So our attention is now on this theorem, proving this theorem. And I'll briefly introduce the Gallai-Edmonds decomposition. So for the given graph G, the Gallai-Edmonds decomposition of G is the partition D1 to dr and A and C on the vertex on the given vertex V. And actually, the usual Gallai-Edmonds decomposition is consists of the partition of the D and A and C part, but I just consider further on the components of D1 to dr. So this is also, since this is also important information. And the D part consists of all the vertices where there is a maximum matching of G not covering B. And A is just the neighborhood of D, and C is the complement of A union D in V. And GDI is a component of GD for every I. Then this decomposition has the following conclusions. So every odd component H of G minus A is vector critical. That is, for all vertices in the component, H minus V has a perfect matching. And this vector critical component is contained in D. And every even component H of G minus A has a perfect matching, and this component is contained in C. And the third condition is the for A prime in A. So for A prime, subset A prime in A, the neighborhood of A prime intersects more than A prime components of GD. And the number of connected components of GD is determined by the size of A and the size of the vertex set and the matching number of G.
So the condition A prime has to be
Yeah. So sorry. Yeah, okay. Yeah. So A prime should be non-empty. Sorry. And I'll just show a brief example. So you can easily see that. So this is a Gallai-Edmonds decomposition of the given graph G, and this red edge describes the maximum matching in the graph G. And actually, we can see that all the maximum matchings should use A and C, and for all the vertices in this D part should have a maximum matching which misses that vertex. And next, so now we check whether this Gallai-Edmonds decomposition satisfies the conclusions. And if we just concentrate on the D part and every component of D, then this is a vector critical because they are all triangles. If we remove a vertex in there, then there's just an edge, so it has a perfect match. And the C part has a perfect matching, obviously, because this is cycle C4. And so we just concentrate on, one can check that actually it also satisfies the third condition with the non-empty condition, but it has a following equivalent condition. So we construct a projection map from this graph to another bipartite graph G prime, such that so it uses the same vertex at A, and it uses a different vertex set, but each vertex in here represent each component of D, and pi is just defined by this. Actually, it is a projection map from this graph to this graph. Now, under this projection map, the followings are equivalent by a host condition. So this host condition implies that for every V in D prime, in this bipartite graph, G prime minus V has a perfect matching covering A. And we call this property a vector critical. And this concept will appear later on. So now I'll briefly sketch the proof of the main theorem. So far, any question? Okay, so
there seems to be a question from the live chat.
Okay.
how does the homology calculation of NMK KN implies the result?
NMK KN implies the result. Okay, that is a good question. So actually we are the homology calculation of the NMKKN implies the result for every graph, if that is what they mean.
So there's a second part of the question. What if we take a simplicial cone with apex over a cycle of length bigger than 3? Then complex is contractible, but link of the vertex is not.
Maybe I can answer the question later. So okay, so let us just give the strategy here. So we take the following divide and conquer approach. First, partition the family of sets into subfamilies and find an acyclic matching there. So actually, we want to partition the family of sets, and we want to partition the family into the subfamilies so that we can understand the quite easily, easily. And we will mainly partition the family with respect to the Gallai-Edmonds decomposition. So the Gallai-Edmonds decomposition becomes important. And secondly, find the joint structure of a given family and find an acyclic matching for each vector. And I'll introduce the joint structure, the definition of joint in the next slide. And so these two ideas are the most important thing. And sometimes we need to use the third ideas. So find the projection map of a given family to a simpler family that we understand more. With respect to an acyclic matching of the simpler family, construct an acyclic matching of the original family such that the projection map restricted to the critical sets becomes an injection between families of critical sets of two matchings. So basically it says the following. So if there is a, so this is a family F. And suppose that there is a projection map from the, there is some map pi to the another family F prime. And suppose that we know how to construct a cyclic matching in this family, in this image family, and there are critical sets like this. Then we can, with respect to this matching and this map, we can also construct a corresponding acyclic matching in here, and such that these critical sets, when we restrict the map pi to these critical sets, this becomes an injection to this set of critical sets. And the size, if we consider the critical set in here, the size satisfies this condition. Actually, as by what I said, the image of the sigma is also critical set, and it satisfies the following condition. Where H is assumed to be, this H is assumed to be where, so H is assumed to be contained in all the sets in the family. And yeah, so we can use these three arguments and merge all acyclic matchings which have been found, and show that they are still acyclic matching. That is strategy. And this is the main idea, the join of the families of sets. A join of two families Fn on F2 on disjoint ground set is defined by the set of the unions where the sigma is from F1 and tau is from F2. And the join lemma states that if we consider the join of the n families having the disjoint ground set E1 to En, then we can combine. If we have found the acyclic matching for each vector, then we can combine them such that if for each each acyclic matching mi, if it has a the set of critical sets, family of critical sets ui, then the acyclic matching for the join becomes the join of the critical family of join of the critical family of critical sets. So basically, so if we assume that we have found all the acyclic matching for the each factor, then we can, and if we have found the upper bound for the critical set for each matching, then we can just sum up all the upper bound for the join. So for the size of critical set in the join. And so there's no. So this is a step. Now we start to prove the main theorem, and this is a step one. We like to find the acyclic matching at the base. And recall that we are like to find the acyclic matching on this FH, whose critical sets have size 3k minus 4 plus h. The initial step first start with the finding of vertex V such that there are a non-neighbor V in H and an H of H non-incident with V. Denote the set of non-neighbors of V in H by W. And let S be a star with a center at V, and it is with respect to W and V, where W is a non-neighbors of V in H, and SG be a set of edges in S, such that G plus E is still in FH, which means that if we add that edge, it has a still bounded matching number less than K. With respect to SG, we define the two families. So the first family is that we can add edges, and still we have the bounded matching number, and F1 is not. We cannot, if we add an edge in S, then this increase the matching number to K. And first we want to find an acyclic matching on F0. And there is something, the lemma, called the cluster lemma. And it says that if there is a poset map from the family to the arbitrary poset, then we can combine the acyclic matching for every inverse image of the vertex in Q. So by this argument, we define also the poset map from F0 to Q, such that Q is defined by just the set of family of graphs G minus S, and we just simply define the poset map G minus S. Then for every G in Q, we can easily see that the inverse image of G is just it is isomorphic to Boolean poset of the size SG, of the size of SG, and with a minimal element G. So actually, we can find a complete matching in here, and we can combine all the acyclic matching by cluster lemma. And so actually, we can further show that if there is an acyclic matching M1 on F1, and if there is an acyclic matching M1 on F1, the union of those acyclic matchings is again acyclic. And I'll skip this proof. And now we start to prove step 2, partitioning F into the subfamilies FD1 to DRAC. So that means that if we just fix the Gallai-Edmonds decomposition and consider the Gallai-Edmonds, consider the subfamilies which consider the subfamily of graphs which shares the same Gallai-Edmonds decomposition. And actually, if we just consider the remaining graphs and induce the subgraphs of remaining graphs, where the vertex set is V prime, where now V is the initial vertex of V is removed, then F consists of all graphs G on the vertex of V prime, where this induce the H part, and so induce subgraph, so H is in G, and the matching number is exactly same as k minus 1, and the d part is exactly w. And the following propositions, so the following proposition and cycle lemma actually implies that if we could find the acyclic matching for each subfamily, this subfamily for each Gallai-Edmonds decomposition, then actually we can combine them into one. And so this proposition says that if a G1 and G2 are two graphs with this containment with the same matching number, then we have the containment for the D part and containment of the D union E. And by using a cycle lemma, we can deduce that this actually the union of the all acyclic matching have been found for each Gallai-Edmonds decomposition is again an acyclic match. And now we concentrate on the each Gallai-Edmonds decomposition. So first we consider the simple situation. If there is edge E in this part, such that E is not an edge in H, then we can use the complete acyclic matching in this subfamily. So the argument is very similar, and this is actually because when we add or delete the edge in between A vertices in A or the vertex in A and vertex in C, it does not change the given Gallai-Edmonds decomposition. So actually, this is a complete acyclic match. So suppose not. So that is that these all edges between A and C is contained in H. Then this family has a following joint structure. So FCDJ is represent the family of vector critical graphs on D1, DJ, DI, which contains H. And the PMC is the family of all graphs which has a perfect matching on C. And so this is just the union of the induced subgraphs of H. And projection means that the family the PROJ means that the family of graphs where by this projection map, if we send the graph with respect to this projection map as I already defined, that graph becomes A vector critical. So we can introduce this joint structure in the given Gallai-Edmonds decomposition, and actually this can be easily done by the Gallai-Edmonds decomposition theorem. So by the joint lemma that I have introduced, we can combine the acyclic matching for each factor in the joint, and that the combined acyclic matching has a critical to bound the size of the critical set for the whole family, we can just add all the upper bounds for the acyclic matching. So for the critical sets of the acyclic matching for each factor. So by their reason, we consider the acyclic so the upper bound for each factor. And it can be shown that for each vector critical, the family of vector critical graphs, we can have this upper bound. So we can sum them up. And for this match, for the family of graphs between graphs consists of the edges between A and D, we use the idea of projection to obtain an acyclic matching. Recall that if we have a critical set, so we can construct a acyclic matching, and the critical set have the size defined by this. And it can be shown that for the image family, we can find the upper bound like this. And if we use this and this, we can conclude this upper bound for the family PROJ. And for the matchings in for the PMC, we can also have the upper bound here. So by summing them up, we can have the desired conclusion. And actually, in the final step, there are also two cases where A union C is an empty set and A union C is non-empty. And so there is a very complicated maximum expression over here, but we don't need to use the maximum expression, but we can just bound this by, for example, H, the size of, so number of edges in H, the induced subgraph H of H on DJ in here. So now we don't need to use the this minus one when this case, but when A union C is empty, by the assumption of the V, there should be an H edge in either D1 or in D2 or D3 or D4. And so some of the DJ should satisfy this condition. So by using this minus 1, we can get the 3k minus 4 plus H for HV prime. And we can sum up the remaining H edges to get a desired bound. And this is the basic proof ideas. So there is very little time to spend to introduce the application to rainbow matching problem. So I'll just go briefly. So by using the Leray result, we can get this collaborative version of the rainbow matching problem. And the statement is the following: if there is a E1 to E3k minus 2 non-empty sets of edges in a graph, such that for every pair, it has a matching number at least k, then there exists a rainbow matching of size k. And the same conclusion, so rainbow matching means that the matching, it is basically matching that each edge is chosen from the distinct edge set in here. And the same conclusion holds for a bipartite graph using only 2k minus 1 edge sets. And this can be proved by the Leray result and using the Homson's theorem like this, stated like this. If a k is a near Leray complex on V, and for a given partition, and let us just define the M be the partition matrix. If M is a subcomplex, and then there exists the sigma, phase sigma, which contains some two edge set, union of two edge set for some I distinct indices. And this is Homson's theorem, and let us briefly see the proof argument. So rather than just considering the edge set, maybe the edge set would not be disjoint. So we duplicate them if they appears in the many different edge set. So for the duplicating the edges, we use the colored edges in here. So the set of E comma I, and we redefine the E tilde, which is the union of all the colored edges. And we define the K, another simplicial complex K, such consisting of all the sigma, subset sigma in E tilde, where the projection of the sigma has a matching number less than K. And we will just a proof sketch of the rainbow matching problem. Let D be 3k minus 4, and let be the partition matrix given by this partition. If there is no rainbow matching of size k, then M should be a subcomplex of k. Yes, so since they have all the matching number of the rainbows, they should be less than k. So they should be so M should be a subcomplex of k. And since so this is our result, and then so by this result we can also similarly the K should also satisfy near the Leray property. And by Homson's theorem, there is a sigma, which implies that the projection of sigma is less than K, which contains some EI tilde, EJ tilde. This is a contradiction because actually it is so their projection assumed to have the matching number at least k, but by this it has a matching number less than k. So this is a contradiction. this is one way to prove it. And so I'll skip many discussions in here, but so I like to just introduce this part. Actually, recently, Aharoni's group, so this is Aharoni, Briggs, Gina Kim, and Mingi Kim, and this is Aharoni, Briggs, Minho Cho, and Gina Kim. And they could found the combinatorial proof of this example with a slight more improvements, and especially for the original motivation for this finding this collaborative version is actually this. And about 2 years ago, we require the 3k minus 2 edge set, such that if we require this condition for each edge set, not the union edge set, but each edge set, to have the same conclusion of a rainbow matching. And this 3k minus 2 edge set, so require the number 3k minus 2 is recently improved to 3k minus 3 by Aharoni, Briggs, and Gina Kim and Mingi Kim. And also they could get this theorem for the slide more improvements. For example, so we require that every set should be non-empty, but they require that the only 3k minus 3 should be non-empty in here. Yeah. So, and also they proved the same result in bipartite graph using the combinatorial argument. So I'm very happy to see that, but I'd like to ask you a question that actually they can we have the purely combinatorial proof for the following corollary? Actually, this corollary can be obtained by the Leray result and using the Thomson's theorem also by the same argument. And actually, the coloring of the edge, the partition of the edge set is replaced by just a matroid here. And so this condition, the condition is now so replaced that for every flat of rank 2, if the matching number is bigger than or equal to k, then there is a rainbow matching of k which is independent in that. So the condition is slightly changed, but it is exactly same condition and same argument works for this corollary.
What's the matching number of matroid?
So this is a matroid on the edge set. So this is a matroid on matroid on a graph. Yeah. So there is a graph, or also there is a matroid in here. And my question is, can we also give a purely combinatorial proof for this corollary? So I'll stop here and skip. Thank you for your attention.
Thank you very much. Any questions?
Maybe I should check the question you.
Andreas answered it.
Okay. So yeah, because okay. Any other question?
Also, one thing I'm wondering is,
yes.
So you're looking at the subgraphs of small matching number.
Yeah.
Can it be generalized to the induced subgraphs with a small stability number, so small alpha, the maximum size of stable set? So if you take a line graph of a graph, then matching becomes a stable set.
Yes. Actually, I think Mingi is doing. So Mingi Kim is doing that research, and he could get some results for that. So actually so as far as I remember, I don't exactly remember, but as far as I remember, he considers some collapsibility rather than de-relaying. But the collapsibility is a little bit more stronger result than de-relay result. So yeah. There is some result like that. So actually, independent. So the family of independent set or the family of the independent. So family of smaller independent set, family of graphs which has a smaller independent set. It is also, I think, quite extensively studied, but I don't remember exactly. So.
Other questions? So there's a combinatorial proof for your main theorem?
Yes.
With the one better?
Yes, a rainbow matching theorem. One.
If there's no other question, let's thank the speaker again.